Okay, so this video picks up right where we left off. We're still on topic 2, and we're going to go into Cartesian vector notation now. So let me pull this up real quick. All right. So again, this is a little bit of a refresher from calculus, but basically what we have are unit vectors in the x and y direction. Okay, what a unit vector is, whenever you hear the word unit here, you want to think of the number 1. Okay, the reason we use the number 1 is because it's basically a freebie number. We multiply it by anything and we just get the number that we multiplied it by. Okay, so a unit vector is a vector, or these vectors here, I and j actually, are vectors that are directly in the x and y direction but have a magnitude of 1. Okay, I should be having little arrows here. I lies directly on the x-axis and j lies directly on the y-axis. So to represent f as a Cartesian vector, all we have to do, so this is, remember, our resultant force, Fr, same thing, right? Fr, all we have to do is take the Fx in the I direction and the Fy in the j direction. And this actually specifies magnitude and direction at this point, right? Again, if we want to separate this into magnitude and direction, we can do this. And get everything we needed. Okay, and of course, the way that we separate it is still by using Fx cos theta, Fy, I'm sorry, not Fy, F cos theta, F sine theta. This is equal to Fx, this is equal to Fy. That's what we plug into this equation, okay? So it's pretty straightforward. We're gonna go ahead and jump right into an example here. Okay, so here I have a link subjected to two forces, F1 and F2, and I want to know the magnitude and direction of the resultant force. So of course, you can use any of the methods that we've come up with so far, okay? I'm actually going to do this first using the scalar method just to show you guys. Okay, so scalar notation means I do the magnitude and direction separately. Okay, so I'm going to sum. I want the resultant in the x direction. Okay, I always want to specify which direction is positive. Okay, I'm going to say the right is positive, and all I need to do is sum the forces in the x direction. And now if I do that, I get the resultant force is equal to, let me come over here and put this into components, F1 cos 30, F1 sine 30. This one's going to be F2 sine 45 because the 45 is measured from the y. And F2 cosine 45. Okay. Now I'm just going to put them here. Cosine 30, it's positive, minus 400 sine 45. And that's just equal to 236.8 newtons going in this direction. And then I'm going to sum the forces for the y direction. Up is my positive direction. That's just equal to all of the forces added in the y direction. And I get the resultant in the y direction is 600 sine 30 plus 400 cosine 45, and I get 582.8. Okay, and my resultant force is the square root of 236.8 squared plus 582.8 squared, and I get 629 newtons, and my theta is just inverse tan of 582 divided by 236, and I get 67.9 degrees, and these are my answers. Okay, Now, I want to show you guys how we can use the Cartesian vector notation, okay? And the reason we actually need to understand this is because when we get to 3D systems, sometimes you have to use Cartesian vector notation because it just gets really messy if you try to use any other notation. So we do have to be familiar with all of these different types of methods for solving. So we did scalar notation, now we're going to do vector notation. So what I'm going to do, let me copy this image. Okay, so what I'm going to do here, I'm not going to actually have to draw on this. You still need those components, the 600 cos 30, 600 sine 30 actually. So I probably should have just left those on there, but you know what? We'll do it again so we get some more practice. 600 cosine 30, 600 sine 30, 400 cos 45, 400 sine 45. Okay, now for F1, what I'm going to do is I'm going to write F1 as a Cartesian vector. So I'm going to take the x component of F1 and say this acts in the I direction, and then I have a positive 600 sine 30 that acts in the j direction. And for F2, I have a negative 400 sine 45 in the I direction, and I have a plus 400 cos 45 in the j direction. And my resultant, of course, is equal to F1 plus F2. These should be vectors. Okay, so how do I add F1 and F2? These are all vectors. I add the x's together, so the 600 cos 30, so all my i's, minus 400 sine 45, this is my I direction, plus 600 sine 30, plus 400 cos 45, and this is my j direction, and I end up getting my resultant vector is 236.8 in the I direction, plus 582.8 in the j direction, and you can see that's what I got here for each of those. And they're positive, which means up and up. To get the resultant, of course, I would just take the square root of both of those squared, and theta just fy over fx. Okay, so pretty straightforward. We're going to do another example here, example 7. Okay, so the first thing we want to do, first part is here, 2-50. We just want to express f1, f2, and f3 as Cartesian vectors. Okay, so again, I'm going to start by putting all of these into components. So let's choose some colors. So we'll do red here for F1, 15 sine 40 because the vertical is given, 15 cos 40. $36 sine 30, 36 cos 30, 26 times, this is now going to be the vertical, right, because I'm using the vertical, so times 5 over the hypotenuse, and this component is going to be 26 times 12 over 13. So first, please guys, make sure that you can solve, or you make sure that you can put all of those into components. That is one of the most important parts in solving this problem. So make sure you take the time to remember how to do this using vector analysis, okay? Now we can go ahead and put all of these into our Cartesian system. So we have F1 is equal to, F1 is the one I did in red, so it's going to be 15 sine 40 in the I direction plus 15 cos 40 in the J direction. You could also just go ahead and directly write the resultant by just summing up those and putting them in the I and J, but this question specifically asked us to write the Cartesian vectors out for each one, which is why I'm doing that. So here I'm going to have a negative 26 times 12 over 13 in the I, plus 26 times 5 over 13 in the J, and my F3 is the purple. So I have a positive 36 cos 30 minus, oops, I forgot my directions. In the I, minus 36 sine 30 in the J. And this is basically the first part of the problem. This is what they're asking for. So that's my first answer. Okay. Now for 2-51, we want the magnitude and the resultant and magnitude of the resultant force and direction measured counterclockwise from the positive x. So basically, magnitude and direction of the resultant force. So all we have to do here is we remember that FR is just the sum of all those forces. So I'm going to start here by putting everything in the I direction together. So I have 15 sine 40 minus 26 times 12 over 13 plus 36 cos 30 plus 15 cos 40 plus 26 times 5 over 13 minus 36 sine 30, and this is all in the J. And I can simplify this, and I get 16.82 in the I plus 3.49 in the J. And I can get the resultant by taking the square root of, remember, this here is my fx, this here is my fy. So of fx squared plus fy squared, and that is just 16.82 squared plus 3.49 squared, and I end up getting 17.17 kilonewtons. And to get my direction theta, it's just inverse tan of 3.49 divided by 16.82, and I get that. So what I'm saying is basically my resultant, I'm going to start with the angle, measure it counterclockwise. That's it. Okay. Okay, so now we're going to move on to Cartesian vectors in 3D. Okay, so you really want to have mastered the 2D system before we kind of get into the 3D system here, because it's actually very similar, just a little bit more visualization is required. So the first thing that we want to kind of discuss is this idea of a right-handed coordinate system. Okay, so I know that we're not in an in-person class right now. I'm doing this via video for you guys, so I really want to try to explain how you can visualize this. So I have a picture here, and what you need to do is take your right hand. Okay, the right-handed coordinate system, basically, you point your thumb up like you're giving a thumbs up. That's going to be your z-axis. Okay, then you want to curl your fingers. So your pointer finger, your middle finger, ring finger, and pinky finger. You want to curl all those fingers with your thumb up from the positive x to the positive y. And that's how you typically want to draw your systems. And that's how you want to decide your positive x, y, and z. So it's pretty straightforward in determining your positives. So I'll show you what I mean. Your thumb should be pointing up like this. The positive x would be here. The positive y would be here. And this is for this class and for most engineering applications, how we will be drawing our 3D coordinate system. And these will all be the representative positive directions. Okay. And in a little bit, we're going to also talk about something called the right-hand rule, which is what we're going to use to figure out how things are rotating and what directions are positive and what directions are negative, but we're not quite there yet. Okay, just remember that our right hand is going to be used to help us figure out these problems in a lot of senses, okay? So here, what I've done is I've put a picture here for you that extends what we've been doing in a 2D system. So if you see here, we've been dealing with this down here. Okay, we've been dealing with just this, which is the x-axis and the y-axis, and this is our resultant in a 2D system here. And now what we're doing is we're adding another dimension. So that's no longer, that A prime is no longer what we're looking for. We're now looking for this final resultant A, okay, that acts in all three directions. So we have an AZ component, we have an AX component, and we have an AY component. Okay, so all we have to do is now, instead of just including AX and AY, we just need to add AZ in. Okay, and for Cartesian coordinate systems, if you guys remember, this would be, right, this is still I, this is still J, and we use a little K for Z. Okay, that's pretty much it. That's all we have to do to kind of extend this rule to Cartesian vectors, okay? These are the unit vectors that I just wrote out here for you, okay? So positive I, positive J, positive K, we determined with the right-hand coordinate system. And of course, our magnitude is exactly the same as before. We're just square rooting the squares of each component. So the component in the x direction, the component in the y direction, the component in the z direction squared, take the square root of that, and I still get the magnitude of A. And then for direction, a little bit different. So I'm going to use something called direction cosines, because now my direction is going to be defined from every axis. Okay, so with a 3D coordinate system, because I'm adding another dimension there, I need to know where my resultant lies in terms of every plane, in terms of every axis. So what I need to do is I use direction cosines. So let me show you what I mean by that. If A is my resultant here, I want to know how far, what is the direction of A with respect to the x-axis, that would be alpha. What is the direction of A with respect to the y-axis, which is beta? And what is the direction of A with respect to the z-axis, which we call gamma? So I'm going to write, these are the little Greek letters, alpha, beta, and this little guy here is gamma. Okay, so still pretty straightforward. All I need to do to get cosine alpha, which is the x direction, I just put the component of x divided by the total, component of y for beta divided by the total, component of z divided by the total. So still very straightforward. We call these direction cosines. Okay. Now, my unit vector, so we can get the unit vector of A, right, in two ways. We can either recognize here that my direction cosines are equal to the components of each one, and that gives me the unit vector of A, or I can directly just put in AX over A, AY over A, AZ over A, and I'll get the unit vector as well. Okay. Now, my cosine squared alpha plus cosine squared beta plus cosine squared gamma is equal to 1. This is a property of my direction cosines. Okay, and these are all formulas that will help us when we're solving these 3D problems. Okay, so let's try example 8 here. The two forces act on the hook here, and we want to specify the magnitude of F2 and its coordinate direction angles so that resultant FR acts along the positive y and has a magnitude of 800. So we want, basically, what we're saying is we want FR. It needs to be 800. That we know. And we need it to act in the positive y, which means it's just going to be 800J. So they're giving us FR. Okay. If I wanted to draw that here, right, like that. Okay. And I'm given the resultant, I'm given F1, so my only unknown here is actually just going to be F2, right? Okay, So what I'm going to do is I'm going to start by putting everything into its respective components. Okay, so I need to first, I'm going to start with just F1 here. Okay, so if I want to express F1 as a Cartesian vector, what I need to do is I need to remember that I have components of F1 in every direction. So I have a F1 cosine alpha 1 plus an F1 cosine beta 1. Sorry, this is in the I, this is in the J, plus an F1 cosine gamma 1 in the K, which these are all my direction cosines, okay, measuring F1 to each axis. That's what I'm trying to do here. Okay, so here I know that I have 300 cosine. What is my alpha 1? Alpha needs to be the I direction. Let's just look at this one real quick. Alpha has to be the I direction. I'm coming to F1. I corresponds to X. What is the direction from F1 to the X axis? It has to be the 45. So this here is my alpha 1. That's how I'm getting that. So 45. Okay. Now plus 300 cosine beta 1 is going to be measured from the Y. That's going to be 60. Plus 300 cosine my angle from the Z, which is 120 in the K. And now I just need to combine all these or simplify them actually. Simplify these into 212.1 in the I plus 150 in the J. And here, actually, this should be a minus, right? This is going down. This should be a minus here. Minus 150 in the K. Right? Because if I look here, the component for F1 is actually going to be going down in the Z. So it has to be minus there. Okay. And this is all, I'm going to put these in brackets so I can make sure I remember this is all in newtons. Okay. Now this is F1. What about F2? I don't know F2. So I'm just going to say that I have some F2x in the I plus some F2y in the J plus some F2z in the K. I have no idea what they are. So now I have my FR, my F1, and my F2. And I know that FR is equal to all the forces, which are just F1 plus F2. If I had more forces, I'd add them. I don't. This is all I have. So what I'm going to do here, I have those three equations. I'm just going to plug them in here. So I know that FR is 800 in the J. I know that F1 is 212.1 in the I plus 150 in the J minus 150 in the K. And I'm going to add in F2x in the I plus F2y in the J plus F2z in the K. And now I'm going to put everything, put all the like terms together, so put all the i's together. So I take the 212.1, I have this I here, plus F2x I, plus 150, this is for the j's, plus F2y, this is the j, minus, I'll do a plus minus 150, plus F2z in the K. And now I'm going to take each coordinate direction. Here I have only a j on this side, which means my I component is 0. And I'm going to equal it to the I component here. So 212.1 plus F2x. And I can directly solve here. My F2x is equal to negative 212.1 newtons. Do the same with the j. The j component on the left side of the equation is 800 equals 150 plus F2y. I can solve for F2y and I get 650 newtons. And I can do the same with k. I have 0 on the left, negative 150 plus F2z and I get F2Z is 150 newtons. Okay, now I can get the magnitude of F2 by taking the square root of negative 212.1 squared plus 650 squared plus 150 squared, and I get 700 newtons. And I can get all of my directions by using the cosine direction. So cosine alpha 2, which is the force 2 measured from the x direction, is just negative 212.1 divided by 700. I get alpha 2 is 108 degrees. Measured from the y-axis here is this. I get beta 2 equals 21.8 degrees. Cosine gamma 2 is equal to 150 over 700, and I get that. So now if I want to draw this out, just so we can see what this looks like, I have my F1 that acts somewhere here. I have an F2 that acts somewhere here. And I have an FR okay, and I was looking for F2. So now my F2, if I measure all of those, I want to show you guys where the gamma, beta, and alpha are. So alpha, again, is measured from the x positive x to the vector. So this is my alpha. This would be the 108 degrees. I'm running out of colors. We'll do beta. This is measured from the y-axis, so 21.8 degrees. And our last one, let's see if I can find a new color here, measured from the z is our gamma 2, which is 77.6 degrees. Okay, and of course our magnitude of that is 700 newtons, and that's it. Okay, so a little bit of work, but pretty straightforward in solving. Okay, the next thing we're going to learn about is position vectors. So you guys will deal with this in dynamics as well, some other courses. But basically what we can do is we can use position vectors to help us in solving for unit vectors and for other problems in a similar way as what we've been doing. So what is a position vector? You can think of a position vector as kind of a roadmap from going from point A to point B. Okay, it's just basically expressing coordinates or point A to point B in a vector form. So what you want to do is we always use R. We typically use R to express position. And it's just going to be the X component, the Y component, the Z component, of course. And the way we find that is if we want to measure from point A to point B, we take the difference in the X, that's our I, the difference in the Y, and the difference in the Z, and that is our position vector to get from point A to point B. And that's literally just like your coordinates, right? So XA, XB, Y, whoops, not XA, XB, what am I doing here? XA, YA, ZA, because we'll do this in 3D, XB, YB, ZB. Okay, this would be if this is in 3D. Okay. Easiest way to show you guys how to do this is actually through an example. So the first thing we want to do, let's read what's happening. So we have an elastic rubber band attached to points A and B, and we want to know the length and direction measured from A towards B. So whenever we want the length here, okay, if you want to measure length, you always want to get the position vector and then take the magnitude. Because remember, length is a scalar, right? Length is a scalar. We don't care about direction. We just want to get the length. It doesn't matter if we're measuring B to A or A to B, it's the same length. So that's why we take only the magnitude of the position vector. Okay, well, to get the position vector, let's write out what are the coordinates of point A. So for point A, I need to go 1 on the x in the positive direction, 0 on the y, because it acts only on the x and z there, you can see, and 3, -3 in the z direction. To get to point B, I need to go -2 in the x, right, the opposite direction, +2 in the y, and 3 in the z. So from this, I can actually directly solve for my position vector, right? Difference in bx minus ba, that's my I, plus the difference in y, that's my j, plus the difference in k. And I end up getting my position vector is -3i plus 2j plus 6k, putting it in brackets and putting it in meters, right? Now my resultant is going to be equal to square root of -3 squared plus 2 squared plus 6 squared, and I get that length is actually 7 meters. Okay. And now I want the direction measured from A to B. So what I'm going to do now is I'm going to solve for my unit vector. My unit vector here, u, is, remember, just r divided by the magnitude of r. So I can just say that's equal to -3, the component in the x, divided by 7, plus, remember, these are the cosine vectors. That's why I'm doing this. I want the directions. This is the definition of my cosine vector. I just take it from the unit vector. And I get 115 degrees, 73.4 degrees, and these are always measured from the positive. So if I'm going to draw those out here, what I have is I have some B and A, and what I'm saying is that this, from the x to it, this is my alpha of 115. Here is my beta. And here is my gamma. Okay. All right. So let's see how much more we have left of this. More examples here. Almost done. Okay. We'll just kind of power through this. So next thing we have is force directed along a line. So just like I can go from point A to point B, I can also use position vector to deal with forces. So F has the same direction as the position vector that I'm using along the line of F, right? If F is directed from A to B, then I can use the position vector from A to B to kind of help us with the force, right? And I also know that that unit vector is going in the same direction. So F has some unit vector in that direction, okay? So I'm going to show you now how we can use the position vector to help us solve for problems with forces involved. Okay, so we have a man here pulling on a cord with a force of 70 pounds. So this man in the yellow is pulling down on this cord with a force of 70 pounds. So you can think of him as F, just kind of a little force F. We want to represent this force acting on the support A as a Cartesian vector and determine its direction. Okay, so I'm actually going to redraw this here. Kind of simplify it from all of the extra fluff that they're showing us. And we have this person tugging on this rope with some force F, which is 70 pounds. And basically what we want to know is we want to know what is the alpha, what is the beta, And what is the gamma? What are these directions? So how can we find the directions? Well, the directions correspond to the unit vectors. Okay, we want the force as a Cartesian vector and we want the direction. So what we're going to do is we're going to start by defining our position vector. Okay, now because we can, let's see where our origin here is. Our A here, in the x direction, we see the difference is going to be that 12. In the y direction, we have that -8. And in the z direction, we have, where is the z? 30, but we have the 6. So really, it's going to be 24. I'm just taking the differences of each of these. And this is in feet. The magnitude of r, right, we're going to square root 12 squared plus 8 squared plus 24. The negatives don't matter because we're squaring. And we get 28 feet. And this actually is the length of AB. This is how long this is how long AB is, not how long the length is. Okay. I'm going to kind of move down here a little. So we can now get the unit vector. This is what's going to help us get the direction cosines by saying it's r divided by the magnitude of r. And I just have 12 over 28 in the I minus 8 over 28 in the j minus 24 over 28 in the k. And what I can do now is I can say that my force here, my Cartesian vector force is equal to the magnitude of F times the unit vector. And this is a formula that we can use. Because remember, the unit vector is just it's a vector with a magnitude of 1 in the same direction of my force. So if my force is 70 pounds, all I have to do is multiply in the unit vector to get my appropriate directions for each one, x, y, and z. Right? So I can say that F is equal to, take the 70 pounds and multiply it in. 12 over 28 in the I minus 8 over 28 in the j. It's just telling me the components in each direction, the proportion. And I get 30 in the I direction, negative 20 in the j. So the unit vector puts forces into components for me. Okay, and now I can also use the unit vector again to solve for alpha, which is just going to be cosine inverse of 12 over 28, 64.4, beta, which is cos inverse of -8 over 28, which is 107, and gamma, which is cosine inverse of -24 over 28, which is 149 degrees, and that's it. So I can use my position vector and my unit vector to help me solve for a lot of these things.